Great, thank you. Tēnā koutou katoa, ko Olive te whakapaparanga mai, engari I tipu ake o ki pakuranga me karanga a hape. Kei Awaroa toku kāinga inaine. Ko Gail Roa, ko Melville oku mātua, ko Rose toku tamu iti. Ko Tanya Killip toku ingoa, no reira, tēnā koutou katoa. Right. Morena koutou. It's lovely to see you here today. Thanks very much for coming along. I hope that you're going to find this interesting. I certainly have found this topic very interesting since I started working on it in the second half of last year. So first of all, I'm just going to share my screen so that you can hopefully see my slides now. Jared, can
That's
you
all
see
good.
them? Yeah,
That's
okay,
it.
great. Thank you. Just thought I'd better make sure before I continue on. Yeah, so I've got some photos here of various different places. So as I said, I grew up in Pakuranga and also spent a lot of time in Cornwallis when I was growing up. There's actually two different schools represented at the top of my slides, which you may probably only notice if you actually grew up in Pakuranga. The left one, the picture of the school, that's Pakuranga College, which I went to in, old school, form 5 to 7. And on the right is the crest for Edgewater College, which I went to in forms 3 and 4. Down the bottom on the left is a picture from Awaroa, Helensville, which is, as I said, where I live now. And it's a very beautiful place full of lots of historic buildings, and I often see it on TV in ads and various different programs. There's lots of filming that goes on around here. And then on the right is my daughter, Rose. Okay, so, whoops. Right, there we go. So as Michael said, today we're going to look at the couple of questions. Why do my students struggle with fractions, and also how can I help them? So in this presentation, I'm going to be looking at 4 different things. Firstly, I'll look at the background to this problem. Secondly, we'll look at the reasons why students struggle with fractions. Then I've got a couple of questions for you to answer, and I can answer any of your questions that you might have at that point, and I'll have a bit of a break from talking. Then we'll look at what research says around fraction learning, and finally we'll look at what you can do to help students based on that research, and I've got some activities from the research for you to have a look at as well. Okay, so let's make a start. Okay, so fractions are a notoriously difficult topic for students. This is not a new issue, as this evocatively titled article shows, and it's also not an issue that is restricted to New Zealand, but has been noted on by academics worldwide. So I think it's important to remember that, you know, it's not just students in Aotearoa that are struggling with this, but students all over the world. However, students in New Zealand do demonstrate great difficulties with fractions. For example, the National Monitoring Study of Student Achievement in 2022 found that only 32% of Year 8 students could correctly answer the question, a half plus a quarter, which obviously is of quite a concern. And I was quite interested in this because I thought, particularly the fractions a half plus a quarter, you know, they're pretty common fractions, and I would have thought that most students would be able to just sort of visualize, you know, what the answer to that question is. So why do students struggle with fractions? Well, it seems to me that there's sort of 3 main reasons. So we'll have a look at each of these in turn. Firstly, the shift from whole numbers to fractions requires a considerable conceptual shift in students' understanding of numbers. For example, unlike whole numbers, fractions have no fixed ordinal sequence. If I name a whole number, then you could name the next whole number in the sequence, right? But if I name a fraction, then there's no kind of next fraction in the sequence for you to name. Also, unlike whole numbers, the magnitude of fractions is not easily determined. So if I give you two fractions and ask you which one's bigger, it's not necessarily immediately obvious, obviously unlike with whole numbers. Furthermore, the magnitude of fractions is not uniquely represented. In fact, every fraction has an infinite number of equivalent fractions. So these fractions initially appear to be different, but actually represent a fraction of the same size or magnitude. So here, for example, the fraction 2/3 can be represented as 4/6, 6/9, 8/12, and so on infinitely. And I think sometimes, particularly like myself as a secondary school teacher, I tend to forget about, these kind of complications with fractions and how different they are in some ways from whole numbers. So this difficulty in the conceptual shift from whole numbers to fractions results in something that's known as whole number bias, or sometimes it's called natural number bias. And this means that students inappropriately use whole number methods to solve problems involving fractions. So for example, a student might say that 2/3 is less than 3/8 because looking at the numerators, they see that 2 is less than 3, and then looking at the denominators, they see that 3 is less than 8, right? Which, it wasn't something that had kind of really occurred to me before, I have to say. But obviously that's not the case. And, if they actually think about the fractions, 2/3 is obviously bigger than a half and 3/8 is less than a half. So obviously 2/3 must be bigger. Okay. This problem with whole number bias also appears often, though, when students do fraction addition problems. And this is what happened in the problem of a half plus a quarter that we looked at earlier in the National Monitoring Study of Student Achievement. Most students who got this question wrong got it wrong because they answered it as 2/6. So obviously they've just added the numerators together to get 2 and added the denominators together to get 6. But again, if the students stop to sort of really think about it, they must realize that the answer cannot be 2/6 because 2/6 is less than a half, and yet the problem is a half plus a quarter, right? So obviously the answer has to be bigger than a half. But obviously students don't seem to have that number sense, that kind of sense of the magnitude of numbers. Whoops. Okay, so the second main reason I think that students struggle with fractions is that fractions have 5 different possible interpretations, and an understanding of all of these interpretations is necessary for a good conceptual understanding of fractions. And it's important to note that, so I call these, some commentators call these interpretations because they're essentially the same. In fact, in maths, they're isomorphic. But the point is they're a different way of looking at or interpreting what a fraction is. So let's look at each of these briefly in turn. So first of all, the part-whole interpretation involves seeing fractions as a certain number of equal parts selected from a whole number of parts or set of objects. So for example, this circle here is divided into 4 parts and 3 parts are selected, so that represents the fraction 3/4. Next, the measure interpretation of fractions involves seeing fractions as a length or distance, typically from 0 on the number line. So in general, a fraction a over b represents a intervals of length 1/b. So in this example here, you can see that we've got the fraction 3/4, and this, you can interpret this as meaning 3 lots of the distance 1/4. And this is a really important interpretation for students to understand. And some research has showed that this is quite a difficult conceptual leap for some to understand the fractions as multiples of unit fractions. Okay, so the next interpretation is the operator interpretation, and this sees fractions as a quantity that seeks to operate on another quantity by shrinking it or stretching it. Now, unfortunately, let me just see if I can move. Oh, whoops, hold on. Sorry for a second. Yeah, so in this example of an operator, so we've got two bars here, and you can see that the shorter bar is the result of taking 3/4 of the taller bar. So the fraction 3/4 has operated on the taller bar to shrink it, right? We can also look at this in the kind of converse direction. If we look at the smaller bar, then and operate on that bar with the fraction 4/3, then we get the taller bar here. So the fraction 4/3 has operated on the smaller bar to stretch it. Okay, so that's the operator interpretation. Next, the quotient interpretation of fractions sees fractions as the result of a division problem. And this is the example that you mentioned earlier. And yeah, I find exactly the same thing at secondary school. And it's like so important at secondary school when students are doing calculations with fractions on their calculators, and then into algebra, which very much sees, fractions as division all the time. So the quotient interpretation sees fractions, yeah, as I've said, as the result of a division problem. So 3/4 is the result of dividing 3 by 4, right? And this is also the same as sharing 3 items equally between 4 people. So each person gets 3/4 of an item. So that's what I've got represented in the picture here. So if you had your 3 items, in this case, they're pizzas, divided into 4, and then if you give one piece of each pizza to each person, then each person ends up with 3/4 of a pizza in total. Right, so that's the quotient interpretation. And then finally, the ratio interpretation of fractions sees a fraction as the ratio between the numerator and the denominator. So in our example here of 3/4, 3 is 3/4 of 4. So I think you'll admit that altogether, this is a lot for students to understand, and obviously, this is a process over a number of years for them to appreciate each of these different interpretations of fractions, and it does make it a difficult concept. Okay, also, as well as these different fraction interpretations, there's also many different types of equipment or physical representations and diagrams or visual representations that can be used in relation to fractions. So these representations fall into 3 different categories. So there's area representations, very often circles, and they could be circular fraction pieces or diagrams of circles cut into pieces, and also rectangles with shaded numbers of pieces as well. I used to use that a lot previously. So area representations naturally link to the part-whole interpretation of fractions, although they can relate to other fraction interpretations as well. The second type of representations are length representations, and these include fraction tiles, fraction walls, folded strips of paper, bar models, like in the Singapore method, and number lines. So these all obviously represent fractions with a single dimension of length. And so these models link well to the measurement interpretation of fractions, although they can relate to other interpretations as well. And then finally, set representations involve groups of objects or counters, and can also be represented by dots or groups of drawn objects or shapes. And here the whole is represented by the total number of objects in the group. And these representations link quite naturally to the ratio interpretation of fractions, although they can link to other interpretations as well. Okay, So now I have a couple of questions for you, and I'm going to take a break from talking for 5 minutes while I give you an opportunity to answer them. So the questions are, do you use equipment or diagrams in your teaching of fractions? And if so, what types of equipment or diagrams do you use? So I'm just going to now add a link to a Padlet into the chat. There we go. Cool. So if everyone could just jump onto that and yeah, have a go at answering the questions, and we will reconvene in about 5 minutes. Okay, thanks. Great. Okay. Yeah, so it seems like there's quite a range of different representations that you guys use, which is interesting. So fraction bars and circles, fraction tiles, circles, multiple shapes. We've got a number of number lines, which is great because that's going to feature heavily in the second part of my presentation. Cool, masking tape on the floor. Awesome. Yeah, there's an activity that I came across in research using tape on the floor and making shapes and doing fractions of those shapes as well, that we'll look at later. Awesome. So a good range there. And I like, yes, you'll see the drawing and dividing up number lines is a really great activity, and there's a number of those in the activities we'll look at near the end later as well. And yeah, it will become kind of more apparent why as we head into the next section of the presentation. Okay, so let's carry on. Thank you for those for that feedback and the answers to those questions. Okay, so now we're going to have a look at research findings, and yeah, we'll look at each of these kind of main topics that have come out of the research or that I've seen in the research. Okay, so firstly, it's generally accepted that a good conceptual understanding of fractions is necessary for students to succeed with this topic. A knowledge of fraction algorithms alone has shown to be insufficient. And in fact, there's lots of research with students' errors in algorithms for fraction computation. So for example, students, common errors are students using the algorithms wrongly or using the wrong algorithm or kind of mixing up bits of the algorithm. Yeah, so that's kind of problematic. However, yeah, both physical and visual representations have been shown to be helpful in building a conceptual understanding of fractions. At one time, it was generally felt that students should be exposed to all three different types of fraction representation. And I mean, this is possibly still the case. But studies have shown that the use of multiple representations can be confusing for students unless each representation is fully understood and connected to the other types of representation. And of course, this takes a lot of instructional time to make all these different connections. And so it may be that kind of focusing down on a few key representations would be best for students. Okay, so the part-whole interpretation of fractions linked to area models has been shown to predominate in instruction, except perhaps in a few Asian countries where, interestingly, the measurement interpretation predominates. Unfortunately, the part-whole interpretation of fractions is problematic in a number of respects. So firstly, the part-whole interpretation doesn't emphasize a fraction as a single number. And it's interesting from research in the States, they've asked questions about like how many numbers there are in a list, and some of those numbers are fractions, and a number of students count the fraction as two separate numbers. So in this case, the 2/8 would be counted as two numbers. They see it as a 2 and also an 8. Yeah, and so because of this, the whole number bias tends to persist. Yeah. Um, Also, the part-whole interpretation of fractions makes it difficult for students to conceptualize improper fractions, as it's not possible to have a fraction that consists of more parts than there are in the whole under the part-whole interpretation. Down the bottom, I've shown it is, of course, possible to have to represent fractions greater than 1 and improper fractions in area models by having more than one whole. So in this case, obviously 2 separate circles to represent, in this case, 9/8. But this is actually a conceptual shift and a move from the part-whole interpretation to the measurement interpretation, because it requires students to see each of these pieces as 8th pieces, and then you're accumulating 9 of those 8 pieces to produce 9/8. So you can see that that's different from, you know, 2 parts out of 8 parts kind of approach. Right. So also the part-whole interpretation of fractions has been shown not to promote a good understanding of fraction magnitude. And we'll look at this a bit later. And this is a really important concept for students to understand, and has been shown to be important for lots of different kinds of achievement in maths. On the other hand, research has shown that a greater emphasis on the measurement interpretation of fractions in instruction is helpful. And this is because the measurement interpretation emphasizes fractions as single numbers with magnitude and makes sense of improper fractions. So you can see an example of the improper fractions up here. So they've got a number line, and they're jumping up in halves, and you can see that when they jump up in 5 lots of a half, they get to 5/2. And it's also, I think, quite easy for students to see then the connection between the improper fraction 5/2 and the mixed number, 2.5, using using number lines like this. Number lines also connect to the measurement interpretation of fractions and help build an understanding of the density of fractions. And so the density of fractions refers to the fact that there are an infinite number of fractions between any two fractions. And so by successively partitioning number lines, students are able to appreciate this idea. And we'll have a look at this a bit later. So number lines have also been shown to be more effective in solving fraction comparison and fraction division problems than area models. Furthermore, the process of constructing common units in the measurement interpretation is the same as constructing common denominators for comparing fractions and for fraction addition and subtraction. And here's an example down here of this. So you can see they've got the fraction a half and a third, and students can see that the common measure for each of those, or a common measure for each of those fractions, is a sixth, right? And so this is taken from a digital or virtual manipulative, but you could also do it obviously with physical fraction tiles. And then also they can take that further and easily see that, so when you're adding a half plus a third, then that's going to result altogether in 5/6. And you can connect these fraction tiles even more powerfully with the number line to kind of further represent this, and for students to further see the effect of adding fractions and how the magnitude changes. Okay, another important point from research is that fraction magnitude understanding has been shown to be key both to understanding fractions and for general mathematical achievement. So Siegler and Braithwaite have argued that magnitude is the unifying property of real numbers, and you can see this in the example here. So their integrated theory of numerical development proposes that numerical development occurs through the increasing understanding of the magnitude of different types of numbers. And so they say that although, as we've seen earlier, that many features of fractions differ from whole numbers, by focusing on the magnitude of fractions, students come to see that all real numbers have magnitude that can be represented and ordered on number lines, as is shown in this diagram here. So we've got a range of all sorts of different real numbers, and they can all be ordered and represented on that number line. So these theoretical ideas about the theory of the integrated theory of numerical development have been backed up by quite a lot of research in cognitive and developmental psychology around students' thinking and development over time. So it's backed up by empirical research. Research has also shown that in order to build an understanding of fraction magnitude, students should be iterating unit fractions. So like we saw on the previous slide with the fraction tiles, and on the number line with counting up in halves. So that's iterating. It's also critical that students understand the inverse order relationship between unit fractions and whole numbers, which is also called the inversion property. And that's that the larger the denominator of a unit fraction, the smaller the fraction, and vice versa. And this is a really common stumbling point for students, and it's really important that they understand that. And that can be achieved through focusing on unit fractions. It's also important for students to carry out successive partitioning of number lines to fully understand how equivalent fractions appear to be different, but can represent the same magnitude. So here's just a simple example of this. Down the bottom, we've got a number line divided into halves, and then you can see if each of those halves is divided into 4, then we get eighths. And then if each of those eighths are divided in half, we get 16ths. And then you can see how the equivalent fractions all take the same place on the number line. So it's emphasizing that they all represent the same number, the same magnitude. It's just that they appear different. And Lemon, as we'll see later in the activities, has a really great arrow notation for students to help them keep track of this successive partitioning. Also, the representation of fractions on unmarked number lines has been shown to be not only a good measure of fraction magnitude understanding, but practice with this has been shown to play a causal role in developing that understanding. So yeah, I'll just stress again that unmarked number lines and students representing fractions on those, yeah, is really important for students. In my research, I'm actually looking at the new approved resources for students in years 0 to 8 in primary school. And I'm noticing a lot of pre-divided number lines, yeah, for students to simply like label, or even pre-divided shapes, pre-partitioned shapes, and students basically just have to color them in. Whereas it would be well, research suggests that it would be a lot better if students were partitioning these themselves. Okay, so how can we help students? So in summary, by developing by getting them to develop a good understanding of fractions by emphasizing the measurement interpretation of fractions, right, over the part-whole interpretation, and also using lots of number lines and more number lines than area models. Also, we can work to improve students' understanding of fraction magnitude by using the kind of methods that we've just talked about for improving them, including getting them to place fractions on unmarked number lines. It's important also that this includes the fraction magnitude of different types of fractions, such as improper fractions. There's been a number of studies where they've been looking at marking fractions on number lines, and many students mark improper fractions on the number line between 0 and 1, which shows obviously a lack of understanding. And also, this will, emphasize the measurement interpretation by using improper fractions, because you can't interpret them properly with the part whole interpretation, as we've looked at earlier. Okay, right. So that's kind of essentially the end of my presentation. But now I've got an activity for you. So as I've mentioned earlier, I've put together a few different activities from research onto a document, which I am going to link in the chat right now. Okay. Right, there we go. So hopefully you should all be able to access that. And then, I'm interested to know, what activities from this might you use in the classroom, if any, and, how you might adapt the activity, for students at different levels and so forth. I think some of them could be quite easily adapted. So I'm keen to know about what you think. I've created another Padlet, which I'll put a link to that in the chat in a few minutes once you've had an opportunity to have a look at the activities. And then if you can, do a similar thing of posting in there, what your answers to those questions. So what activities, you might be keen to use from that, and how you might adapt them. And then I think, because there's not that many of us here today, I think it would probably be quite practical for us to have a bit of a discussion. Happy to answer any questions. Great. So if you want to make a start on that, I'm just going to stop the sharing, if that's okay. There we go.
My first sort of main question is, what years would you be aiming these activities for? Often, as a secondary school teacher, often like we have students coming in at year 9 that don't have a good grasp of fractions.
Yes.
Should this be more implemented with younger students to increase
Yeah.
their ability before they get to secondary school? Or?
I mean, ideally, but I've kind of put a range of activities in there. So the first ones from Zhang are definitely more like primary sort of school ones, although you could easily like adapt a few, like maybe the baseball one or something, and do them at secondary school, but maybe just like as a quick starter or something, to kind of, see where students are at, and and maybe as a kind of quick way of dealing with any sort of issues that you notice are arising.
Prior knowledge and misconceptions.
And students understanding. The activities from Le Mans are significantly more challenging, and I'm really keen to try out some of those activities with my students next year. In particular, there's one I really like about finding, oh dear, oh, maybe I didn't include it. Oh, here we go. Yeah, finding fractions between unit fractions. So name 3 fractions between a quarter and a third. There's lots of different ways of doing that, and they raise some really like deep and great thinking about about fractions, because it requires them to have quite a deep knowledge, I think, to be able to.
That actually looks like a really interesting, a rich activity, although on the surface it looks basic. I've just marked a exam paper from a scholarship calculus student, and they had to graph some hyperbola for different values of k, and I gave a sketch with k equals 0 and k equals 1, And naturally the students go to k=2, but it didn't fit on the grid I gave them. And a number of these top students just gave up and said, well, what are we doing? Not thinking that they could try different values of k between 0 and 1. Like,
Right.
I was like, oh dear, so I need to revise fractions with my top students.
Oh dear. Yes,
Yeah.
yes, yes,
Whole
that's
number bias.
quite interesting. Yeah, that's quite interesting. I've had a similar issue with different kinds of graphs. I used to do an activity, I think it's called like Marble Run or something on Desmos. Yeah, and yeah, students, yeah, again, not sort of thinking about the fact that, you don't just have to deal with whole numbers, that there's numbers between them.
I think I know what you're talking about. That there's like you draw straight lines, the marble slides, and then
Yes.
the gradients, they go up in 1 or 2 or 3, and then the students need to get it to be a fractional gradient, a half, but they go to 0, and then some of them go to negative. But
Yes.
they skip a whole range of numbers.
That's it. That's exactly the one. Yes.
Yeah.
Okay.
Did anyone else want to share their input into this? It's not just me talking. Or you're going to set up that Padlet, aren't you?
Oh, yes. Oh, sorry. I'll put the link to the Padlet on. That might be a nicer way for people to share than if they don't.
Yes. Yesterday in class, we're looking at the scale of the human universe, which is a website. If you Google it, you can find it, and you can zoom into like the smallest things that exist, or you can zoom out and find black holes and stuff. And the idea that when you zoom in or zoom out, you get really, really small or really, really big numbers. At a year 10 boy going, "Sir, what's a yoctometer? Is that an American unit of measurement?" The zoomable number line's pretty neat, though.
Yeah, that's really cool. That's awesome. Yeah, I was just having a quick play myself. That's really cool.
I just was about to throw out some measuring tapes because they've come off the windy bit, but I'm thinking that I can use those bits of tape to apply some fractions working now.
That would be really awesome. I'm really interested. I've been reading, kind of about textbooks in different countries and so forth. And it's really interesting. A number of the Asian textbooks, including Japanese textbooks, really focus really heavily on measurement when they're introducing fractions and doing fractions. And it sort of occurred to me after a while, oh my goodness, yeah, because it's like any kind of scale of measurement you've got is essentially a number line, isn't it? And so yeah, so I reckon tape measures and
Yeah.
scales and stuff are really good ways of looking
And
at
because they're
fractions.
the windy ones, they're foldable, so they can fold them in half for those three
Yeah.
quarters. Yeah.
Yeah, that's really cool. That's like that activity with the rope and stuff on there,
Yeah.
eh? Yeah,
Yeah.
yeah. It
Yeah.
makes it practical.
Yeah.
I think
Cool.
using tape measures and stuff as well, like I'm sure I'm not the only one that finds students really struggle to draw their own scale on graphs. Like that, and with coordinates, they often count the bars rather than the gaps. So I can understand why people have got pre-made number lines. That you said that you've noticed pre-made number lines rather than students making their own, because it's a speed thing. We also know that at least the number line will be accurate. But yeah, having students divide things up themselves, I needs a lot of work, I think.
Right. Yeah, that's really interesting because yeah, I thought a lot of those resources for approved resources for year 0 to 8 students like come in two parts. There's a textbook or an online thing, and then there's a workbook that they can write in. So you think, well, there's actually a lot of opportunities with a workbook that are being like funded by the government, one to one for students, to have those kind of activities where they're drawing and dividing and like, yeah, creating these things themselves, and yet they don't seem to be there, which, yeah, I found kind of surprising. But certainly, if anyone's interested, if you look at Lamont's book, the chapter on measurement interpretation, she does a lot of work with students dividing up number lines from a reasonably young age, and she talks about the fact that initially they're not even divided that well, but but don't worry about that, they get better over time. And also I reckon there's a lot of learning even in just like dividing things up, because like, for example, if you want to divide a number line into sixths, I mean, well, there's different ways of doing it. I mean, you could start dividing it by thirds, but I'd probably start by dividing it in half and then dividing each of those halves into thirds, because, like it's not easy to make the divisions equal. And actually there's quite a bit of maths in that. And are students missing out on this maths if they're not like dividing the number lines themselves?
Even just paper folding, like making triangular prisms like out of a piece of paper, and finding that the students don't know how to fold the paper into thirds, like, or even measure it in half. They're using a ruler to measure. I'm like, why don't you just fold the paper?
Yes.
But you just have the whole number bias thing around, like that. You use an example of 3 pizzas, 4 people, which students cope with. 4 pizzas, 3 people, students usually cope with that as well, even though it's top heavy. But then when you bring in context where it's like, you're never going to say a context like 3 pizzas for a quarter of a person, but you might say like 3 people, a quarter of a pizza, like, so when you're breaking up fractions into fractions, and if students still think it's like whole numbers being divided, they find that jump really, really tough.
Yeah, I think that's a good point. And I think that's another thing that's really easy on number lines. It's really easy to find fractions of fractions on number lines by just, dividing up dividing up those fractions further, and it makes a lot of sense. And if they're used to partitioning the number lines, I could see that that's like not such a difficult thing. Yeah, and with division of fractions as well. Yeah, number lines I think are really, really helpful.
Anyways, Tanya, this session's got 5 more minutes left. Did you have anything else you wanted the participants to do? I see the Padlet. A few people have commented on the Padlet.
Cool. Okay. Shall we just have a quick look at the Padlet? So we've got, finding fractions between a quarter and a third is a nice way of integrating measurement. Yes, I agree. And I think there's lots of different ways you can do that in different levels. You can do that with, you could give them fraction tiles, for some students as well. And other students could be working with folding number lines, or, drawing them and dividing them up. Cool. Turtle Race could be adapted to many contexts. For example, download bar for a game. Yeah, that's cool. How much of the game has been downloaded? Yeah. And I think that would be more appropriate for sort of maybe some older students. Get the students to show their benchmark fractions like a half and keep dividing to work out the precise points. Yeah, that's awesome. Yeah, I agree. That's cool. I think the rope and water activities are accessible for students struggling with fractions. I like to do baking too. Yeah, I reckon baking's a really cool concept. I often think of it like with cups and stuff, half a cup, quarter of a cup, a third of a cup, and some experience with that. That's really going to help with understanding that a third is bigger than a quarter, and so forth.
I think there's those measurement, like you can actually buy them where it's like a third of a cup is shaped like a third, like as a wedge.
Oh, right. Okay.
I've seen those. I haven't got them myself. I don't trust my baking ability to bake for my students. So, but the turtle race one's an interesting thing. One of my groups in stats this year did an experiment where they had loading bars of a game, and with one group, the loading bar went really fast initially and then dragged to a finish, and the other loading bar, the student coded this, was really slow initially and then sped up. And they asked students a simple question of perception of time. How long do you think the loading bar took? And both loading bars were exactly the same time, but they just had different speed curves. and our perception of like how far what fraction has gone by is influenced by how long it took to get there as well. It's kind of interesting.
That is interesting. Yeah, cool. Right. Has anybody else got any questions? No. Okay. Great. Well, oh, cool. Thank you, Annie.
On that note, then I'll share my screen and we'll just finish up the session.
Great. Well, thanks very much, everyone.
Just to let you guys know about a couple of events that are coming up. Hopefully the dates are right on these. One sec. Can you see my slideshow now, Tanya?
Yep, I can.
Cool. So there's a few events coming up. Obviously, the NCA change consultation's closing on Monday. So if you want to feedback to that, or your department wants to feedback to that, it's closing then. We've got another AMA online session in term 4. We've got another workshop in about 5 minutes as well. AMA Maths and Calc Teachers Day, which we put on for our region, but often have teachers coming from outside of Auckland. That's at AUT on the 24th of November. Stats Teachers Days is a little bit later in the piece this year, so hopefully you'll still be able to attend if you want to.